Okay, so let's discuss some logic gates. Okay, so first we'll discuss AND gate. So AND says if okay, so AND gate is used for two or more variables. So let's take two variables A and B. So it says if A and B is true, then the output will be true. Okay, so true is denoted as 1 and false is denoted as 0. Okay, so in AND gate, let's if two variables are there, the possible values it can take are 4. That is 0 0 0 1 1 0 1 1. Okay, so it says if A and B is true, that is A is 1 and B is 1, then only the output will be 1. Okay, otherwise it's all 0, because here if you see both are false, here one is false, here one is false. Okay, so only when both are true it will give 1. Okay, then let's discuss NOT gate. So NOT gate is only a single operator. There will be only one variable, and if one variable is there, possible value is 0 and 1. So what it will do is invert that value, so the output will be 1 0. Okay, so if we take AND gate and if we put a NOT gate in front of it, we get NAND gate. Okay, so NAND gate will be complement of AND gate. Okay, so whatever values we got here, 0 0 0 1, all this, okay, it will become complement in NAND gate. So for 0 0 it will become 1, for 0 1 it will become 1 1, then 1 1 is 0. Okay, that is an AND gate. Then let's go to OR gate. So OR gate says that if A is true or B is true, then it will give output as 1. Okay, so here you see both are false. First one 0 0, so it will give 0. Okay, now if A is 0 but B is true, then it will give 1. If A is true, B is 0, again it will give 1. And if both are true, again it will give 1. Okay, so NOR will be complement of OR, so it will look like this. Okay, now comes XOR. So XOR means exclusive OR. Okay, so it is derived from OR gate and it's exclusive in one case. So XOR works like if and only if one of the variable is true, then only it will give 1. Okay, so if you see A and B both are false, 0. Okay, now A and B, one is true, right? Like B is true, so 1, and 1 0, only one is true, A, so 1. Now A and B both are true, so it becomes 0. Now if you compare the OR gate with exclusive OR table, you can see only this portion is different, correct? If you see that, that's why it's exclusive OR. Otherwise the other three values are same. These three values are same as these three values, and this last one is different. That's why it's called exclusive OR. And exclusive NOR is complement of XOR, so it will become 1 0 0 1. Okay, and these gates are represented like this: AND gate, AND gate.
Here's what I found.
So AND gate will look like this, NAND will look like this, OR will look like this, NOR will look like this, not look like this, only one, and XOR looks like this, XNOR looks like this. Okay, now let's see Boolean function representation. Okay, so two types of representation is there: standard form and canonical form. Okay, so what happens in standard form, if we see in SOP, that is sum of products, if you see here it looks like sum of products, right? There are products y bar, z bar, x, z, and there are sum of it. Okay, so it is sum of products. So if you notice here, it's a function of three variables x, y, z. But if you see this answer here, you can see x, y, but there is no z. Here x, z is there, but there is no y, and here y, z is there, but there is no x. So this is in form of standard form. In each of the term, there is one of the variable missing of this function. That is standard form. Okay, and product of sum, same. If you see, three terms are there. In each three terms, one of the variable is missing. In this one, z is missing. In this z is missing, and here x is missing. Okay, then comes canonical form. Okay, so canonical form is important. So in sum of product, if you see, it's a function of three variables. If you see, three terms are there, and all the three variables are there: x, y, z, x, y, z, x, y, z. So this is a canonical form. In product of sum, three variables are there, three terms, products of sum. So here also see three variables, three variables, three variables. Okay, so steps to convert from standard form to canonical form. Okay, so it's always desirable to go from standard form to canonical form. Okay, so the step is each term which is there, multiply by the sum of the missing term and its complement. Okay, for sum of products. So it will be like, if there is a function, if x function consists of x and y, and the answer is x, and clearly you can see this is a standard form. Okay, now I want to convert it into canonical. Okay, so what we do is, x into 1 will give me back x. We are not adding anything. Okay, so what we are doing, we are multiplying by the sum of the missing term. Now in this y is missing, so we are multiplying by sum of missing term and its complement, which is added. Okay, so we get xy plus xy bar. Now it's in canonical form. Now if you see, xy is there in both terms. Okay, for the product of sum, if it has two variables, okay, and answer is x, we want to convert it into canonical. So what will happen is, in previous case we were multiplying it by 1. In product of sum, we add with 0, because it will not create anything change in the answer. So what happens, we add with the missing term multiplied by its complement, and that will give us canonical form. Okay, so let's discuss min terms and max terms. Okay, so it is also one representation. So min terms is equal to canonical sum of products. Max term is canonical product of sum. In min term, variable is considered as 1 and its complement is 0. But in max term, variable is considered as 0 and its complement as 1, denoted as sigma small m, here denoted by pi capital M. Okay, min term, max term. Okay, so let's take two variables. Okay, a, b. Let's take two variables a, b. So the possible values it can have 0, 0, 0, 1, 1, 0, 1, 1. So in min term SOP, it will look like this. If you see, variable is considered as 1, okay, and its complement is 0. Okay, so here min term SOP is denoted as this. Since 0 is a complement, variable complement is 0, so 0 is a complement, so we write as a bar, and it's sum of products. Okay, so products with the last letter, so we have to make products, so it will be a bar, b bar. okay, represented as small m with 0 here, okay, min term 0, okay. Then again here a bar because a is 0, and b because 1 is variable considered as 1, and it's denoted as m1, okay. Similarly it will be a b bar, and that is m2, okay. Then there is a b m3, okay. Now in max term, if you see, the last one is sum, so you have to make sum. And in max term it is opposite, variable is considered 0, complement is 1, okay. So first one is 0 0, so it will be like sum we have to do. Here we did product, so here sum. So 0 is considered as variable, so it will be a plus b, okay, and this will be m0. Then it will be a1 is complement here in max term, so it will be a plus b bar m1. Then it will be a bar plus b m2. Then it will be a bar plus b bar m3.